Hi friends, this is Daniel from Moralis, and today we're going to talk about a very important topic, reentrancy. Reentrancy is an old problem. The most infamous hack in Ethereum, the Dao Hack, triggered a lot of discussion on this subject back in 2016. But is it still relevant? Well, just last year, the Burgerswap hack for $7.2 million, the SurgeBNB hack for 4, and the Cream Finance hack for 18.8 all had a reentrancy exploit component. Reentrancy is actually a very simple concept. It happens or could happen whenever an smart contract makes an external call to another contract. When an external call is made, the execution of the EVM is passed from the initial contract that made a call to the contract that was called. Unless this contract has full knowledge of the code of the contract that was called, then that external call is not safe, because this contract could do anything it pleases with that EVM execution. It could call another contract, it could execute a logic inside of its own scope, which most of the times is the intended result that this contract expects, or it could return and call this contract once again. And this is what is called a reentrant call. This call can become exploit if this contract that made the call has some state that has not been updated and should have been updated by the moment that it made this call. On this video, we are going to see an example of a reentrancy example. We are going to exploit it ourselves. We are going to go beyond the example to check what are other cases that are not that obvious where this might happen. And we are going to fix the vulnerability in our example. Follow me to it. We're going to start with the practical part of our video, and we are going to check out this contract that I just deployed and also verified. We have it in the snow trace, which is the same as Etherscam but for Avalanche. This contract that we have here has a balance of 27 AVAX. We are going to contract. The license, not very important. We can check here the structure of the contract. We have the name, which is escrow unsafe. We know that it's going to be unsafe because it's what we are going to exploit. We have the events, which we are going to cover by the time that they are triggered. We have these nonce, which later on we're going to see how this nonce is used. We have this address owner. This is something that I have added to this contract in order to be able to execute this function. Purely for convenience, guys, because you might make mistakes when you are practicing. This function will allow us to have a way to withdraw any funds that are in this contract if we are the person who deployed it. But is not relevant in a production scenario or in a real contract. This most likely wouldn't be there. Now we start with the actual contract. So we have an struct that is the escrow object, and it has several elements. We have an amount, which is the balance of the escrow. We have a depositor and a beneficiary. The depositor will be the person that is putting funds in the escrow, and the beneficiary is the person that will be able to withdraw the funds if the escrow condition is fulfilled. And how do we know that? Well, an approver has to come, which is a third party that will verify that the condition of the escrow has happened or not. And when this happens, then this Boolean approve will be set to true, and the beneficiary will be able to withdraw the funds. The escrow can end in two ways. It can end by the beneficiary withdrawing the funds when the escrow has been approved, or can end with the depositor canceling the escrow. And when each of those things happen, then this active will be set to false. It will be set to true when an escrow agreement is created on this contract. So This is an abstract infrastructure for escrows that will allow to create as many as they are needed. We have a mapping of bytes 32 to the escrow object, which is our escrow registry. And the constructor is only for the helper function that we mentioned before, so not important. And we have here the deposit, which is our main function of the logic, where we can set a beneficiary, set an address, and it's payable because through this function we put funds in a contract. I want to stop here to make a little note to you guys. Contracts can only receive native tokens in 3 possible scenarios. Through a payable function, which is what we have here. Through a general payable function, which is an special keyword that is called the receive function. And that receive function can receive certain data, and it will be that function that is triggered whenever the contract receives funds. And that's going to be very important for our analysis later. So just for you to know, if a contract doesn't have any payable functions, it can still receive native tokens, in this case AVAX, but also ETH or Matic, depending on the network that you're in, only when it has a payable function or when it has this general receive function to manage those deposits. There is a third scenario, which is, let's say that the contract doesn't have a payable function or doesn't have any receive function that covers the general case of funds being received. Then it is going to call a fallback function, which usually is triggered when there is a function call to the contract that doesn't match any of its actual functions. Then that fallback will be triggered to give some return value or some trigger some logic, most likely for error management. And that function might also trigger when a contract receives funds. If this doesn't exist in a contract, that contract cannot receive native tokens. You can force the contract to receive native tokens, but that will be another type of exploit that we're not going to cover right now. Now, this is a payable function, so it will receive funds and will define who is the depositor, which is the message sender, and the amount, which is the message value. Then it will create the ID with the nonce that we have here, that at the beginning is going to be 0. And it will pack that with the depositor address and then apply the hashing function to get our bytes 32, that is our escrow ID. Then just populate each of the elements of the struct with the corresponding values, increase the nonce, and emit our deposit receive with the escrow ID, the depositor, the beneficiary, the approver, and the amount. If you were the owner of this contract, you would set most likely a listener to figure out what is happening in your application. And if that's the case, Moralis is a very good way to track and index contract events. Now, let's check the other function, which is approve, right? And that's this approver would approve that the escrow condition happen. And it's very easy. It will just check that whoever is calling this function is actually the approver, will check that the escrow is active, and then it will set the approve of that specific escrow to true, and then emit an event. We are going to check now the 2 functions that will withdraw funds. We have the cancel escrow, which is the one that the depositor can trigger once the contract has not been approved, and it will return the funds to the depositor. And we have the withdraw funds, which is the one that will be called by the beneficiary after approval. So this withdraw funds, which is the one that we're going to see in detail, will check that the beneficiary is the one calling, will check that the escrow is actually active, and will check that the escrow is approved. When those conditions happen, is making a call to the beneficiary, which could be a contract or could be an account, just a simple address. And most likely the reason this contract is being set up with this way of call and including a value on the call and basically no message data is in order to allow composability. If you implement other type of functions such as this transfer that we have in our helper function over here that will also transfer funds, we are not allowing composability because what is going to happen at that moment is that if a contract receives that, will not have enough gas to do anything, because this transfer function limits the amounts of gas that are sent as an stipend to the recipient to continue the execution of the workflow. In this case, it might be intentional that we want to give that recipient more allowance to do whatever they need to do on their side if the recipient is a contract to actually implement some logic upon receiving the funds. But that makes it a little bit dangerous, and I will explain why later on. Here we have the escrow amount being reset to 0 and the escrow active to false. Then here, since we are calling it in this way, we have to manage any error. So this call is going to return true if it was successful and false if it was not. We are going to require this transfer is actually successful to complete the execution, and then we emit the event. The execution for canceling the escrow is actually exactly the same. The only difference is that we're going to confirm that the escrow is not approved and that the escrow is still active and that the caller is actually the depositor. A very simple contract here. Now, why there is an exploit that we can perform here? And that is because there is a vulnerability that is introduced by an unsafe external call. Since we are receiving the addresses of the beneficiary and the approver as parameters here, that means that those addresses could be anyone, and that contract could have any content. So that means that we are not in control of what that contract will do. And when we forward this call to that external address, if it is a contract, we are basically passing the execution of the EVM to that external contract that, as we already saw, we have no knowledge on what is the code or the logic of that contract. And also, as you remember that I mentioned at the beginning, the contract could have some receive function that is of general scope, or a fallback function that will trigger to receive native tokens. And actually that will be a prerequisite to deal with this call here. So we have a problem, because on that fallback or receive function, that contract can execute any logic. And as we saw in our definition of reentrancy, part of the logic that could be run is re-entering or recalling our contract. So if that specific recipient does that and calls withdraw funds again, then it will again transfer the balance of the escrow, which at this moment it has not been reset to 0. And also will check that the escrow is active, which is going to be the case here because we are setting to false down here. So it's going to continue re-entering these functions all the time until something fails. And if the contract, or in this case an attacker, knows what is the balance of the contract, which is very easy to know, and knows what is the actual deposit that they made, they can just set a very easy logic here to continue calling these functions until they deplete all the funds in the contract and not only the escrow that was created. So friends, we are going to start with our exploiting of our own contract. First, we will copy the information from the contract that we have deployed. We are going to copy all the functions, and the reason we're going to do that because we need to interact with this contract through another contract in order to exploit it. For representing the contract and be able to interact with it, we need to have an interface. An interface is very easy to build. We just need to have all the functions are the types, which we call the function signature. We have our interface ready here. We just need to add a little bit of boilerplate, which is our license and the compiler version. We are going to use the same boilerplate that we already have. Let's paste these 2 lines over here. That's it. Then we just give it a name. We're going to call it interface escrow. We add some alignment here. That's it. We have our interface created. Now we can start by building our attacker, and for that we're going to need the interface that we just created and also the boilerplate that is signaling the license and the compiler version. What we are going to do here is create an attacker contract that will exploit our main contract. In this attacker contract, we want to be able to withdraw the funds after the exploit. So this part is for making it ownable. Then after that, we are going to create the variables that we are going to need. We're going to have one of type escrow that's pointing to the interface, and we call it escrow. We're going to have a uint, which is going to be the deposit that we make, and we're going to have a bytes 32, which is going to be the escrow ID of the escrow that we're going to use for the exploit. Now, if you notice, there is something missing here. We need the interface that we just built. So we import escrow from interfaces escrow interface. That's all. The constructor is just to make it ownable. So owner is equal to the message sender of whoever deployed this contract. This owner will be able to withdraw the funds inside the contract, as we are going to define later on. We are going to define our function attack. Our function attack will take some parameters, the ID of the escrow, and also the address of the victim contract. This is because later on, when we fix the vulnerability in our contract, we will try to attack other contracts with other addresses, and this will make that a lot more convenient. This function is of course external. It is the one we're going to call to attack. What we're going to do here is define that the escrow is going to be the victim escrow, and we're going to define that the attacked escrow ID is equal to the escrow ID that was submitted. We're going to find that the deposit is going to be equal to, as you guessed, the deposit that was submitted beforehand, and this is just linking that deposit that was outside of this contract to this contract in order we perform the attack. This contract is going to perform the exploiting of the escrow very easily once we define that we are going to call escrow withdraw funds with the corresponding escrow ID. That's it. Now we're going to define another function here, which is going to be the one that we are going to execute when the exploit is completed. We call it transfer balance, and it's going to be also external. For this, we're going to require that the message sender is the owner. Then let's do address payable owner is equal to payable of the message sender. Remember that the only way to send native tokens to one address is that the address is payable. So we're going to make this address payable owner, and we're going to do owner transfer address this, which is the address of this contract, balance. Then we're going to create a function that we call receive. If you notice, I didn't add any function keyword here because this is just a default function that Solidity has that's called receive, which is used to manage the reception of funds by a contract. We are going to make it external and payable, and we're going to define an if inside of it. We are going to call the address escrow balance, and this will give us the balance of the contract in native tokens. If it is greater or equal than the deposit, which is the quantity that we are defining here when we define our attack, we are going to call escrow withdraw funds with the escrow ID that was provided. Here is where we are exploiting the reentrancy. I want an event when this happens, so I will put this event here. I call it exploited. This event exploited is going to have an address, which is going to be the target, and a uint, which is going to be the balance. So basically, after we finish the exploit, we are emitting this event. So let's explain our exploit. We are going to deposit with our own wallet some amount in the victim contract, and we're going to do that by defining the beneficiary of the escrow here as the address of the attacker contract that we're going to deploy soon. We're going to define that the approver is ourselves, and then we're going to send, let's say, 1 AVAX as a deposit. Then, in this contract, from here, we are going to execute the attack function with the escrow ID that was created in the victim contract when we created our deposit, and the amount that was deposited, which is going to be the 1 AVAX that we just deposited. This is going to execute the withdrawal function. But as we know, that function in the victim contract has an external call, and we can hijack the execution at that precise moment. So we are able to re-enter, and that's what we're going to do with the receive function. The balance at that moment is going to be exactly the same, so it's going to continue entering recursively until this condition is not true anymore. The condition being the balance is not greater than our deposit. At that moment, it will stop, and the entire balance of the victim contract, which are the 27 AVAX that it has right now, is going to go to the attacker contract. Then we just have to execute the transfer balance function to conclude the exploit. Let's do it. The first order of business is deploying the attacker. We're going to compile it first, and now we're going to deploy it. For this, we're going to connect to injected web3. Let's deploy it. So here it is, my attacker address. I will copy that one now here in the victim contract. I will go to write contract and I will deposit. So we're going to have that contract that we just deployed as the beneficiary, and the approver is going to be my own account, which is this. I want to pay an amount of 1 AVAX, so I want to deposit now. Let's connect to Web3 here. Here we are connected, so it is working. Let's send the transaction. Here we are sending as a deposit 1 AVAX. It was already processed and it has the logs. We know that when the deposit is successful, it's going to create an event that is going to be this, deposit received, and the first index field is going to be the escrow ID. The first one actually is the entire signature of the topics of the events with the index 0. We want to see the actual hexadecimal value of the escrow ID that we created, which is this here. The victim contract has 28 AVAX, which is adding the one that we just sent. Now let's go back to our attacker contract, and we're going to set the attack. So the escrow ID is what we just copied. The victim address is the address of this contract over here, and the deposit, and this is the part that we have to be careful because this is in way and we want to have the integer unit. So we're going to send 1 plus 18 zeros. We have the deposit correctly set. I need to get this expro approved. So let's go to the victim contract again and let's connect to Web3 again. Let's approve it. It's okay. We have the escrow ID already approved. Now we can exploit the contract. Let's go to transact here and let's do it. Let's tag, done. Let's check the logs for this. Since it was a recursive attack, we have a lot of events. This event here was triggered every time that we record to the same function. Now the only thing that is pending is transferring the balance. I will let you know here that I had the amount of 41 AVAX in this account. This contract, if we refresh right now, has 0 AVAX. Our exploit actually worked. Now let's transfer the balance. The transaction went successfully. Let's check it back here and let's check our own account. It's still pending. Successful. Here I got my balance increased. This is the way that you can exploit this contract. However, we're going to do the right thing. We're going to fix it. The next part of our video is going to be using 3 possible strategies to fix this contract. Since performing the interactions that Remix offers us might be a little bit cumbersome, we're going to create a nice dashboard to test as a user of the escrow agreement, and we're going to compare with an attacker. We are going to confirm that we can execute functions as a user, but we cannot exploit as attacker. We are going to use Moralis, and Moralis is very easy to use. You sign up totally for free if you are new, and if you are already a member of our community, you can log in with your existing credentials. In this area, you can create a server. There are a lot of parts of the Moralis SDK that you can use without a server, but that will be not taking full advantage of the Moralis ecosystem. For the little dashboard that we're going to build to make our testing, we actually don't need a lot of complex functionality. If we require it, this is the place that you could get your URL and your application ID. Let's go to create our little dashboard. For our testing, we're going to create a little dashboard. We're going to have a target escrow area where we're going to post the address of each of our different iterations of the escrow agreement as we implement different ways of fixing the reentrancy vulnerability. In this area, we're going to be able to do two things. We're going to be able to make a deposit and also make an approval. These are both actions that happen at the target escrow level. We're going to have as well other two sections for testing as a user and as an attacker. In these sections, we will interact with different versions of the escrow agreement contract, either as a normal user or as an attacker. Our goal is that our fix allows us to interact as a user but not as an attacker. In our logic, we have here some boilerplate to initialize a Moralis server. If we wanted to make this dashboard a little bit more sophisticated and interact with the database functionality of Moralis, we would need to fill out this part. We have here some plain vanilla JavaScript where we set up the address of our attacker contract, which is the one that we have already deployed in Remix, and its corresponding ABI. We are going to do the same with the user contract address, which is going to be very similar to the attacker, but we are going to eliminate the maliciousness that we introduced in the receive function in the attacker side. We also have the escrow ABI of our original escrow agreement. This we are not going to change because we are going to iterate on our original escrow by changing the way that we are executing our withdrawal functions. And this won't change the ABI as it is merely an interface. We have a little login functionality here, which we are using to initialize Moralis and setting the network to Fuji testnet of Avalanche, which is the place we are going to be working. We have functionality also for performing a deposit, for performing an approval, and for withdrawing and attacking. All of these functions work in a similar fashion. We are getting some values as parameters from our HTML form. These functions, for depositing, for approving, for withdrawing, and attacking, are just taking these values, passing them as inputs in the options of our Moralis execute function API, and then the Moralis SDK is solving the call for us without having to do any of the heavy lifting that Ethers or Web3 libraries would require us to do due to manual encoding. For payable functions, you can include a message value, which is what we are doing in the deposit function, for example. And then if you need to get the transaction receipt, you can call this transaction await, which will resolve when the transaction is confirmed. Any UI that depends on those transaction receipts will be relying on this functionality. Here I'm getting the escrow ID to use it in an alert window. Once we have this running, you can just run your Python server, which is what I have done here, calling the Python module HTTP server, which mocks an internet server. Here I can go to check my dashboard. We're going to start our fixing of the vulnerability, and for starters, I want to describe the user contract that we have here. This user contract is actually quite similar to our attacker, and the only difference is that the receive function in this one is more innocent than the one that we had in the attacker. The user contract is just accounting for the amount received, recording how much native tokens it received from the escrow. This is something that is very innocent and actually that is expected to occur in this receive function. Then we're going to set the escrow ID paid to true in this mapping that maps escrow ID and the amount that we received. As mentioned, this is a very innocent functionality. We're going to leave this one alone for now. Now, the objective of our testing is that we are going to create different versions of our escrow agreement that are intended to work when we execute them as a user, but if we try to attack them, as we were doing before, they are not going to work. To fix this contract, we need to get the code. So we're going to go to contract and code here, and we're going to copy exactly the entirety of its contents. We're going to take that and we're going to paste it in Remix. Now let's start by opening a file here, which we are going to call fixed. One of the ways to fix this contract is very simple. Instead of transferring funds through this call value operation, we're going to use a transfer operation instead. When we use transfer, what is going to happen is that instead of opening all the gas that was provided from whoever started the transaction to the called contract, only a limited amount of 2,300 units of gas are going to be allowed. This will make the call more secure because there will be not enough gas to do something much more complex than triggering an event. The problem with this approach, and the reason it is not commonly used currently, is because the actions that client contracts might need to execute might be similar to what our user contract is doing. Something like getting some data into a mapping or loading some data from a mapping. Those operations used to be cheaper before the Istanbul hard fork of Ethereum. When the price of those operations increased, some contracts were broken because they didn't receive enough gas to perform operations that they were routinely executing before. Using transfer instead of call value is actually good only if you are sure that the Ethereum addresses where you are submitting the funds are not intended to be contracts but regular Ethereum accounts. Now, to fix this, we are going to do something very simple. Instead of performing this call, we will just make the receiver address payable and then transfer the escrow amount with transfer. We are just making the caller a payable address, we are transferring using transfer instead of call, and we are sending the amount. We take this require out because the transfer function actually manages errors for us, so it's a lot more convenient in that sense, and this is done. This is one quick fix, but this will only allow us to have very limited functionality in the case the escrow beneficiary is a contract. Let's compile it, fixed 000, and then deploy it. Our transaction was sent. I forgot to change the name of the contract, but that doesn't really matter. We're going to copy the address and paste it here in our input target address. Then we're going to do the following. We're going to make an initial deposit here, and we're going to deposit tokens. We're going to have my own address as the beneficiary. The approver is also going to be my own address, and I'm going to deposit 17 AVAX. We have it here. We're going to wait for the notice and the escrow ID to come. We're going to take note of the escrow ID because we're going to need it later. Now that we have deposited this 17 AVAX, we know that our fixed contract has a balance of 17 AVAX precisely, and we're going to try to exploit it to get those funds. We are going to deposit 1 AVAX. We're going to set the beneficiary as my attacker contract, which I have here in my Remix environment. I will set the approver as myself, and everything is set. I will create this other escrow, and I will try to withdraw the entire amount of funds in this new contract by just executing this escrow with the attacker as beneficiary. Let's do that right now. We're going to paste this escrow ID here to approve it. We have the escrow approved. Let's open the development tools here, and we're going to do the following. We are going to attack now. We need the escrow ID ready, and we need the deposit amount, which is 1. We're going to try to attack, and we cannot. the execution is reverted by MetaMask, sending us this RPC error. The reason is that we are trying the reentrancy without enough gas to execute any complex operation. So as an attacker, we cannot exploit this contract. Right now, we are going to try to execute another deposit, but we are going to set our user contract as the actual beneficiary. So we're going to copy this address. The parameters are going to be the same. It's just that it's not going to be an attacker. We're going to deposit. We got our new escrow ID for this test, and we're going to have to approve it. Of course, because we want the beneficiary to take an action on it. And we have the approval. Right now, we can test as a user. We're going to try to use our user contract to withdraw the amount of funds deposited in this escrow ID, the one that we created just now. And let's try to withdraw, and we get the same error. So as you can see, the fix that we deployed worked, but it will only work when we are executing as an individual account, not as a contract. Our user contract here was totally rejected. Now we're going to go to that latest contract that we deploy, and we're going to withdraw funds directly from there with the escrow ID that we got at the beginning. We withdraw our AVAX. We're going to withdraw funds, and we're going to do it right now. Only approved escrows can be withdrawn. That one was never approved, but we can cancel it. So let's cancel it right now. This is the first one, the one that we deposit, the 17 AVAX. Done. This is just to show you that this contract actually works when we are executing not as a contract that might have certain functionality, but as a regular account. In that case, it works perfectly. Now, if we go to the address of this contract, only the two AVAX that got stuck because we were testing with contracts as beneficiaries are still there, either as a user contract or as an attacker contract. This didn't really work. For recovering those two AVAX, we are going to execute the transfer balance function, which is our cheating function to recover funds that are stuck. This cheating function will never be there in a real implementation. It is in this one because we need to be careful that we can recover our testnet funds. If I go to my account, I can see that I have all the resources that I had when I began testing. Now we're going to do something more interesting. We're going to do another fix, but a fix that will not block us when we're using this as a regular, well-behaved user. Follow me to it. To start with this fix, we're going to copy the entirety of this contract code once again. We're going to go to Remix, and we're going to create a file here that we're going to call fixed01. We're going to paste the entirety of the code that we just copied, and we're going to start working on it. This one is not needed. Now, let's start working on this. We're going to make the type of fix that is what we should have done according to best practices since the beginning, implementing the checks and effects pattern. First, you perform your checks, and then you execute your effects. In this case, the external call is an effect, and these are the checks. We're going to pass this external call to a place in the code that is after we perform the checks. We are not going to send the value of the escrow amount because we are setting it already to 0 in this place, and we need to do something else then. We need to create a temporary variable to hold that value while we have already resetted, and that's the value that we are going to use to implement the transfer. What we are doing is saving the balance of the escrow at this moment, then we reset it to 0, and then we are sending an amount equal to that value here. What is going to happen if the recipient tries to re-enter is that, first of all, the execution is going to stop because the escrow is not going to be active. But even if we didn't have the check for verifying the conditions of the escrow here, the value of the balance of the escrow would have already been reset to 0. So that's all for this fix. It's actually quite easy. We are going to deploy this contract since it is already compiled. It went as with the previous case with the wrong name, but it's not relevant. We copy the address, and to begin with, we are going to interact with the new contract with this address that we copy here. I will send, let's say, 60 AVAX as an individual just to give it some meat. And here I have my escrow ID, which I will copy for later. Then I will try to exploit the contract, getting this AVAX out. My attacker contract is going to be the same, so I'm going to set my attacker here, and this is the attacker, and let's paste it over here. This is going to be the beneficiary, which is the first parameter. The approver is going to be myself, and then I will deposit 1 AVAX. MetaMask is popping up, and we have my escrow created. Now I will approve it. It is approved. Now that it is approved, I could just attack with my attacker contract. Let's go, attack. And we got the RPC error with the execution reverted. The execution has failed. That's it. We were not able to attack the contract. Now let's try to do the same, but with my escrow user. So we're going to set the user here, and I will deposit 2 AVAX right now. Now we have another escrow created, and I will approve it. We got the approval. Now I will try to withdraw the deposit as a user. My MetaMask is popping up. That means that this will work. The escrow was withdrawn. Right now we can go to check the original address of this fixed escrow here and see that the balance is the 60 AVAX that we sent first, 1 AVAX that we sent as an attacker, and 2 AVAX that we sent as a user that we immediately withdrew. That withdrawal should appear here in internal transactions. Yeah, 2 AVAX were transferred out. So that's it. We got our funds out. We were not able to attack, but we were able to use, which was our purpose. This is a part that we have not covered yet. Reentrancy could happen also in other scenarios, where spotting it might not be as straightforward as it has been in our example here. External calls might not be obvious. There are certain tokens and certain transfer functions that will verify if the recipient is authorized to receive certain type of tokens. These type of transfer functions are very useful from the user perspective because it helps to avoid tokens being locked in contracts that cannot manage them, but also the way that this confirmation works is by triggering a function in the contract that is receiving the funds. This also is an external call. So these assurances that are present in some token standards such as the ERC 7077 or safe transfers that are implemented in certain NFT standards require extra care to avoid reentrancy. The checks and effects pattern is your best friend. It helps you to cover your back. Other part that I want to comment here is the way that we are generating our IDs is by only using the nonce and the depositor's address. And as you might have noticed, in all our implementation of the escrow agreement, we are getting the same escrow IDs. It will be better if we make those IDs more unique. And if we introduce another element in the escrow ID generation process, we will achieve that. I have not done it here, but that's very easy to change. We will review just another way to fix this issue and we will be done. We are going to check the third way in which you can avoid reentrancy, and this is by using modifiers and a mutex pattern. This modifier is actually available in the Open Zeppelin library. Right now we're going to explore how it works under the hood. We have a modifier here that is called non-reentrant. The way this modifier works is by checking a log status. This is a variable. The modifier will check that the value of the log is different than entered. If it's equal to entered, then it will reject the call with the message reentrance call rejected. When the log status is different than entered, the first thing it will do is to set the log to entered, and then it will run the body of the function. This is the meaning of this syntax here inside modifiers. After it runs the logic of the function, it sets the log status to non-entered again. We use this modifier in the following way. In this cancel escrow function, we have this non-reentrant modifier here. This is equivalent to adding this require at the top and then setting the log to enter. Even if the way that we are performing this call here is not following the checks and effects pattern, which we are doing on purpose in this case, this log would have changed to entered when the function was called the first time. If the contract that received this call tried to re-enter, it will stumble into this require, which will check that the log status is equal to enter, and the transaction will revert with the message over here. This is called the mutex pattern. The log status is being set here at the beginning with this group of contents. Not entered equal to 1 and entered equal to 2. We have this as a private log status. The reason we are implementing this with integers and not with booleans is because it allows us to have certain gas benefits. This is a little bit more performant in that sense, so that's the reason it's integers and not booleans. We can compile this one and we can go ahead and deploy it. Now we're going to test. Let's make the deposit of the initial funds that we're going to try to hack. We set our own account as the beneficiary and our own account as the approver. We're going to send a lot of AVAX as deposit. We're going to go to the attacker. We're going to get to the attacker address here, and we're going to paste it into the deposit area as the beneficiary. We're going to deposit 1 AVAX. We should get the escrow ID soon. We're getting the escrow ID now. We're going to copy it. We're going to get the approval. We wait for the approval to come. It came. Now we're going to get this escrow ID and we're going to try to attack it. We get the rejection from MetaMask saying that the execution reverted, and that's what is expected because our mutex pattern should have caught this type of reentrancy. The reentrancy is not possible with our attacker. Now let's try to do something with our user. We're going to set the user as the beneficiary here. We're going to deposit 1 AVAX. We got our escrow back. Now we can copy the escrow ID and approve it. And we're going to proceed to the approval. Done. And we can input this as the escrow ID in our dashboard. We try to execute. We see our MetaMask is triggering, so that means it is working. We have our message. The escrow was withdrawn. We're going to go to the transaction and we can see that the AVAX was transferred as an internal transaction. That means that we got the correct behavior. Now we can go back and cancel the original escrow that we set up in our contract. Here, I will cancel that escrow to get my AVAX back. And that's also to confirm that as a regular user that is not a contract, everything is working fine. I'm done. I got my 60 AVAX back, and the only thing that is pending is the AVAX that I sent as an attacker. I will call the function transfer balance. Also, my user contract still have some AVAX, so let's transfer the balance of that one as well. I have all my AVAX back in my account. I want to restate that this mutex pattern is good for you in order you have certain assurances. But if you need to have a log that you need to share between several functions, implementing this pattern can become very tricky and cumbersome, and it is very easy to mess it up. As a general rule, when you're doing external calls, including when you are transferring tokens in any type of transfer scenario that triggers an action in the recipient contract, you have to be very careful because the recipient contract might override the standard functionality you are expecting. If you don't write it, you cannot be sure of what is going on there, and that might give you headaches. So I always use checks and effects. I hope that this video has helped you. It's a little bit long, but thank you for remaining with us. Remember that all the code in these labs is available in the GitHub repository in the description of the video. And remember that we built our testing console thanks to Moralis. Go to check moralis.io, sign for an account, check all the APIs that we have there for you. Also, if you are a developer and you want to join us in this journey, check talent.moralis.io. We're going to be very happy to have you in our team. Thank you very much. See you guys in the next video.